In this video, we are going to continue talking about enzyme kinetics. Understand that the reaction rate, in other words, the velocity for an enzymatic reaction can be thought as a concentration versus time plot. In this slide, we have the particular reaction in which our substrate or reactant, glyceraldehyde 3-phosphate, is going to be converted to the product, dihydroxyacetone phosphate, by the enzyme triose phosphate isomerase. Now, if we look overall what happens throughout time to the concentrations of our substrate versus product, then it makes sense that over time we're going to see a decrease in the amount of substrate and an increase in the amount of products, because overall in the systematic reaction we are going to be converting from substrate reactant to the product. Now, if we take the same reaction of triose phosphate isomerase and now we plot what is the reaction rate or reaction velocity, but we do it at constant substrate concentration, and then we have just a varied, basically an increasing amount of enzyme added to the reaction, we see that the rate of the reaction is going to increase linearly, because the more enzyme we have, the faster or an increase in the rate is going to be observed. Now, when we have in reality an enzymatic catalyzed reaction, or an enzyme catalyzed reaction is the term that I'm looking for, what we see is that the enzymes act with their substrates in a non-linear fashion. So when we look at this, let me just introduce how we actually view an enzyme catalyzed reaction. The capital E stands for enzyme. The capital S is the substrate of the reaction. ES is going to be the enzyme substrate complex. And P is the product of the reaction. Now, when we look at an enzyme catalyzed reaction, you see that the enzyme and the substrate meet. Now, this is going to be reversible. And it basically means that when the enzyme and the substrate meet each other, understand that that substrate has to basically come into the active site of the enzyme, but it has to have the right location, conformation, the right energy in order to then that enzyme substrate complex to commit to make product. Now, one of the things that I want to highlight that it is important to note is that, remember, because our enzyme is our catalyst, enzymes are not consumed or destroyed in the reaction. Because remember, since your enzyme is your catalyst, it needs to be produced to go back and continue catalyzing other reactions. Now, as I mentioned a few moments ago, enzymes react with substrates in a non-linear fashion. So many enzymes have what is called the Mckaylen's Mentin enzyme kinetics. And this is just based on the scientists that found out these discoveries. So as you can see in the bottom, this illustrates what really the relationship between the substrate And the reaction velocity looks like at a constant concentration of enzyme. Because what happens in reality is that when we have a specific enzyme catalyzed reaction, we are not going to be varying the amount of enzyme. What we tend to do is increase the availability or the concentration, I should say, of substrate overall, and then we see the following pattern. So, when it comes to Mckaylen's Mentin enzyme kinetics, we should establish that there are two different kinetics orders that we see. At first, under these conditions, understand that we are going to see first order kinetics, which means that the rate of the reaction is going to depend on the concentration of the substrate, followed by zero order kinetics. And during that zero order kinetics, as you can see, the rate of the reaction does not depend on the concentration of the substrate. Overall, our enzyme is going to have its maximum velocity, which is known as Vmax, and you can see the dotted line on the top. Now, because we can plot enzymes that are going to be following this kinetic pattern as initial velocity versus substrate concentration, understand that the reaction velocity is going to be given by the equation in which we say Vmax times the concentration of substrate can be divided by the term Km plus the concentration of substrate. And as you can see, the names for each one of those symbols is in the bottom right corner of the slide. Now, let's actually understand more in detail of what this information gives us in terms of enzyme catalyzed reactions. So, I already established that the relationship when an enzyme is following Mckaylen's Mentin kinetics is going to be nonlinear. And the equation itself, as you can see, is going to be hyperbolic. Okay, that's why we have this curve. Remember, we have the two different order kinetics in this curve. So, one of the things that need to be established that it is very important to understand is that in this whole process, the Mckaylen's constant, which is the Km, okay, it is a reflection of the affinity of the enzyme for its substrate. So at times you will see that when people look at Km, if the value is really low, it says, or it suggests, I should say, that your enzyme has a high affinity to its substrate. In general, the Km is a characteristic of a particular enzyme substrate system. And overall, the Km is, as you can see, the concentration at which we have reached the half of the Vmax for our kinetic curve, or for the kinetics of the reaction. The reason is that, remember, when you are in this system, still the concentration affects the kinetics, or I should say the velocity of the reaction. So that's why we are looking at half of Vmax, not the full Vmax, because at that point the maximum velocity has reached. So we're really, the enzyme, the substrate concentration is not really affecting overall the velocity. So again, Km is going to be the concentration of substrate at which we have reached half of Vmax. So in general, because we think of Km being a reflection of the affinity, the smaller the Km value, the more strongly an enzyme binds its substrate. Now, understand that because the relationship or an enzyme that follows Mckaylen's Mentin kinetics has a hyperbolic curve being generated, we can actually convert it into a plot in which now the relationship is linear. And that gives rise to Lineweaver-Burk plots. Understand that these are going to be widely used to determine the important terms in enzyme kinetics, such as Km, Vmax, okay? And they used to be used greatly. They are still being used, I should say, in science. Now, understand that in these plots, the y-intercept okay, is equivalent to the inverse of the Vmax, and the x-intercept of the graph represents -1/km. Now, in this course, we are not going to be observing or analyzing Lineweaver-Burk plots, but I just wanted to introduce that these plots do exist to also look at the Km and Vmax values for a particular enzyme catalyzed reaction. Now, we are now going to proceed to talk about how enzymes are going to be interacting with those substrates. And they do by one of two models. The first one is the lock and key model. And in the lock and key model, the substrate fits into the active site perfectly, like a lock and a key. So there are some enzymes that actually use this model system in order to be interacting with their substrate. Now, there is another model that is a little bit more dynamic, which is known as the induced fit model. In the induced fit model, understand that the enzyme is going to undergo conformational changes once it interacts with its substrate in order to accommodate it and then catalyze the enzymatic reaction. Now, understand that when it comes to enzyme catalyzed reaction, this is just a review. Enzyme catalyzed reactions are going to have a substrate, an enzyme. Then once they bind together, they are going to be making an enzyme substrate complex. Then understand that after the reaction has happened, whatever the enzyme is going to catalyze, in this case is illustrating a cleavage, then we have products that are released and we are going to regenerate the enzyme. But understand that in this process, remember that when we go from enzyme substrate complex to product, in this drawing, these arrows are going to be, even though they are shown as reversible, they are technically not. They are going to be going into product once the enzyme substrate complex is committed to making the product itself. Now, one of the things that I want to illustrate is that enzymes at times need some help in order to catalyze their reactions. So in section 7.8 in the textbook, there is a discussion about coenzymes. Okay, so understand that some enzymes, not all, are going to utilize coenzymes or cofactors in order for them to be able to catalyze reactions. So understand that if you have an enzyme that requires a cofactor or coenzyme, okay, so when the enzyme is by itself, the protein portion that it is inactive because it doesn't have the cofactor or coenzyme is called as an apoenzyme. Once that apoenzyme combines with the coenzyme or the cofactor, then that is known as a holoenzyme. And now your enzyme is activated to interact with the substrate in order to convert it to product. Now, one of the things that you can see here is that cofactors tend to be cations. So if we look at the list here, magnesium, manganese, iron, copper, zinc, calcium, cobalt, they are going to be metal cations. When it comes to the coenzymes, understand that some of these are going to be derived from vitamins, but they include NAD+, NADP, FAD. These are going to be nucleotides, derivatives. And we're going to be talking about nucleotides in later chapters. And at times, because these coenzymes are going to be specifically involved as electron carriers, many of the coenzymes that are interacting with a particular enzyme are there because the enzyme is going to be involved in oxidation reduction reactions.